So substrate for nucleophilic substitution and elimination is a haloalkane, as we already know. So haloalkanes are great substrates for nucleophilic substitution and elimination because of the bond polarity between the carbon and the halogen here. So that makes the carbon to have a partial positive charge. And anybody knows what's the second reason for haloalkane to be good substrate for nucleophilic substitution and elimination? You guys remember that or not? No?
It's a good leaving group because it can hold the negative charge. It can stabilize with the negative charge, if I'm not mistaken.
Uh-huh, very nice. So that's the reason why. So because halogens are great leaving groups, uh, that makes haloalkanes to be great substrates for nucleophilic substitution and elimination, right? So this is the electrophilic carbon here, and this is the halogen. And then we know that we got two reactions that are competing here basically. So one reaction is the nucleophilic substitution where the halogen is replaced by a nucleophile. So that is the classic nucleophilic substitution reactions, reaction number two. So I'm going to use the curve arrows to show the substitution here. Um, mhm. And then another option that we know that is always competing with this is beta elimination, which is always competing with substitution. And in that case, the base is reacting instead of with the carbon, the electrophilic carbon is taking um, a beta hydrogen. So remember I said in class, you will get as many elimination products as non-equivalence beta hydrogens you have in the molecule. In this case, there is only one set of beta hydrogens, so we only get one product. So, but you got to keep in mind that there might be cases where you got two sets of beta hydrogens, and in that case, obviously you get two different elimination products. So let's write product here, pretty simple. Okay. So nucleophilic substitution and elimination are always competing. We know this already. And then the whole point of this chapter is for you to see a reaction of a haloalkane with a base and determine whether what's the major product of that reaction, right? And as we discussed in class, the way to do this is by, first of all, identifying the mechanism. So first of all, you need to identify the reaction mechanism. As we know, it could be uni or bimolecular. That's first. And the criteria for to determining if the reaction is uni or bimolecular is simply the base, right? So you're always gonna determine if a reaction is unimolecular or bimolecular by means of how strong is the base that you're using in that reaction. So if we use a very strong base, and strong bases are those that are negatively charged, we're gonna have a bimolecular reaction. If you have a weak base, weak moderate bases, in that case, so we're gonna have in the presence of a unimolecular mechanism. Examples of weak moderate bases are simple. I said in class, we have basically water, low molecular weight alcohols, and low molecular weight carboxylic acid. Strong bases are those that are negatively charged, mostly all of them. So it's relatively easy for you to identify that. So guys, when you look at the haloalkane as a substrate and the base being strong right away is bimolecular. If the base is weak, right away is unimolecular. Now you need to know both mechanisms, right? So bimolecular could be SN1 or I'm sorry, SN2 or E2. So once you determine that it's bimolecular, the next step is to determine whether you're in the presence of an SN2 reaction or an E2 reaction. Nucleophilic substitution, bimolecular nucleophilic substitution, or bimolecular elimination. So the way of doing this is by looking back at the structure of the haloalkane, right? So we discuss how primary haloalkanes will give primarily SN2. We talk about the SN2 mechanism. Remember, it's a single step reaction. That single step reaction implies the bond breaking and bond forming is happening at the same time. And so you need a strong base for that. The exception for this, for primary, the exceptions for this, keep this in mind, are sodium amide and potassium terbutaoxide. These two always give E2. So we discussed that in class 2. Okay. So E2, so SN2 single step, remember factors controlling the reaction, the reaction rate is static factors. That's why remember it's a backside attack. An SN2 reaction is a backside attack. So you basically need the nucleophile to be able to reach the electrophilic center, and that's why the reaction, the reactivity for SN2 reaction follows the order primary, more reactive than secondary haloalkanes. We can never ever have an SN2 reaction over a tertiary, it's too bulky. Okay. So any questions in regards to SN2 reactions? So once again, strong bases, bimolecular, primary haloalkane, mostly SN2. Exception are these two that I have here. Everything else is going to be SN2. Why? Because the backside attack is primary or easy for the nucleophile to access the electrophilic center from the backside. Now, E2 reactions are always competing with SN2. Remember once again, so if you look at the structure of the haloalkane and you see it's a tertiary haloalkane, we know already that tertiary haloalkane will never react through SN2, so they will produce primarily E2 products. Things that we need to know about SN2, there is a reactive conformation, which means that the leaving group and the hydrogen must be anti-coplanar. So that's very important because that determines the stereochemistry of the final product, or could also be depending if it's cyclohaloalkane transaxial. So that's the reactive conformation for E2 reactions, and it forms an alkene, right? So that's the final product. And the deal here, most confusing thing for you guys was what happened when you have a strong base, and then instead of being a primary or tertiary, we got a secondary haloalkane. So if you got a secondary haloalkane, we know they can react by both SN2 and E2. So we need to look again back at the Lewis base and determine if that base is a better base or a nucleophile. The way to do this is just looking at the pKa of conjugate acid of the base. So if the pKa is below 11, you're always going to get SN2. If the pKa is above 11, you're always going to get E2. It's very simple to remember the ones producing E2, but because I gave you only 4 examples in classes, for example, so one of them was alkoxides. So alkoxides, the conjugate acid of alkoxides are alcohols. The pK of alcohols is about 15. So alkoxides always will produce E2 for secondary haloalkanes. You also have hydroxides. Hydroxide is always going to produce the conjugate acid of hydroxide is water. Once again, pKa above 11. Obviously, sodium amide, which is one of the strongest bases, and sodium amide is always giving E2 no matter what. And you got acetylide ions, which will also give you E2. The conjugate acid of an acetylide ion is an alkyne, and the pKa of an alkyne is 25, so above 11. So this is
Professor, excuse me, I apologize. Would we have to memorize any of these pKas, or would they be given to us if necessary?
I can give you pKs if necessary, but again, this is precisely why I'm doing this with you now, because these four bases. You should be able to know that they are very strong bases, all of them. Everything else is going to produce SN2 with a secondary haloalkane. Okay. So, so that's how you. So once again, you see a haloalkane that is reactive toward nucleophilic substitution or elimination. First thing first, identify the mechanism. If a strong base is bimolecular, and now you need to distinguish between SN2 or E2. Primary, mostly SN2, except for these two. Tertiary, only E2, no option for SN2. Secondary depends on the base. This base is E2, everything else SN2. So things that you need to know in regards to the mechanism, details. So that once again, SN2 is a backside attack. If you happen to be doing an SN2 in a secondary carbon with a chiral center, you get reverse configuration. For E2, always reactive conformation. The leaving group on the hydrogen must be anticoplanar or transaxial. So that allows to explain, particularly for secondary, if you get cis, trans, and lastly, for E2, particularly for these two guys, for E2 reactions and regiochemistry, so you always get, remember, you get as many two products as non-equivalence beta hydrogens, highest, so the major product for E2 is always, is the highest substitute alkene. The exception to that is once again, potassium terbutaoxide. Potassium terbutaoxide, because it's so bulky, is gonna give you the opposite, right? So potassium terbutaoxide always E2 major is lowest substitute alkene. Okay. So any questions with bimolecular mechanisms? No questions with bimolecular mechanisms?
No.
So if you get a weak base, or it's a solvolysis reaction, that is a unimolecular mechanism. So all these are solvolysis reactions. So the unimolecular mechanism, the unimolecular means first order reaction. It also means that in the slower step, there is only one molecule involved, which is haloalkane. So step one, slower step, is always formation of a carbocation, right? Something we discussed in class extensively. That's step one. Step two, always a unimolecular mechanism. Potentially is going to be a rearrangement. So you always have to ask yourself, is it a rearrangement possible? And what the driving force for a rearrangement is always forming a more stable carbocation. And the factors making carbocations stable, as we said, are hyperconjugation, inductive effect, and resonance. Mhm. So you gotta always keep in mind rearrangements. I'm gonna say here 2.2a for rearrangements. So we are always got three types in we discuss in class: high dry shift. We also study methyl shift and alkyl shift, which is basically a ring expansion. So this was the three examples of rearrangements that we discussed in class. So it's just practicing this. And so once we got the rearranged product, if there is a rearrangement, if there is no rearrangement, that's fine. The step 3 is formation of both nucleophilic substitution and elimination products. We know they're going to be forming the elimination nucleophilic substitution SN1 and E1. Remember, they always coexist because they share the slowest step, which is formation of a carbocation. So once a carbocation is formed and rearranged, step 2, which is elimination and nucleophilic substitution, is going to happen very fast. So you're going to get a mix of both nucleophilic substitution and elimination. So things to keep in mind for these two, for nucleophilic substitution. So what you keep in mind, if you create a chiral center, so you will get a racemic mixture because carbocations are sp2 hybridized trigonal, which means that the nucleophile can attack from top and from the bottom. For E1 products, you get as many E1 products as non-equivalents. I am recording this, by the way, so you don't need to write it. I will post it on for the people who were not able to attend. So as many E1 products as non-equivalents beta hydrogens. You get the major product, E1 product is the highest substituted alkene. Because once again, like alkene stability determines the radiochemistry of that reaction. Okay. So this is how you should go about with unimolecular with nucleophilic substitution and elimination reaction. So once you see once again the haloalkane, identify the dominant mechanism. If it's a strong base, it's going to be bimolecular. If it's a weak base, it's going to be unimolecular. Once you identify the mechanism, focus on the subsequent steps. Formation of a carbocation, guys. So something was in the exam. Very few people realize if you get a carbocation, it's stabilized by resonance. So meaning it's in an allelic or benzylic. Okay. Oh, is there a potential rearrangement for that carbocation forming a more stable carbocation? And we talk about the factors stabilizing carbocations, hyperconjugation, inductive effects, and resonance. We saw rearrangements of hydride shift, methyl shift, and ring expansions. And once the carbocation is formed and rearranged, if that happens, then the next step is going to be both nucleophilic substitution and elimination products. They always coexist because they share the slowest step. SN1 products, you need to keep in mind the stereochemistry. If you happen to create a chiral center, you get a racemic mixture. E1, red regiochemistry, the major product is the highest substituted alkene. So that's basically chapter 9. Anyone has any questions with regards to this?